I'm Majji. Thank you for attending my talk. In this talk, we will look into the effect of various modes of hydrodynamic interactions on the microstructure of shared colloidal gels. Colloidal gels have wide range of applications in various industries like pharmaceutical industries, foods, paints, consumer care products, and 3D printing. And this is due to their interesting properties that they display. These gels are made of colloidal particles dispersed in solvents. At rest, these particles make viscoelastic networks to give solid-like behavior, and in shear, they break into clusters and display fluid-like behavior. These materials also exhibit yield stress and thixotropic rheology as well. We are interested in studying microstructure and how it affects various bulk material properties as it helps in designing better materials and industrial processes to handle those materials. Colloidal particles can have a wide range of surface characteristics. For example, fused silica, cornstarch, coffee particles, casein, micelles, dairy, and virus particles. All of them have rough surfaces where interparticle friction is important if one wants to simulate their suspensions. And in cases where you have porous particles and particles with polymer brushes on them, the lubrication force may not be that significant. With such variety of surface characteristics, we wish to know how these particles behave under flow. So to simulate these colloids, we solve the discrete governing equation for particle motion, which has the following components. The underlying flow component, the potential gradient scaled with the hydrodynamic mobility tensor, the Brownian noise that satisfies the following two conditions. One, the mean being 0, and the other one, covariance satisfying the fluctuation dissipation theorem. We have 3 different modules, each with different combination of hydrodynamic modes turned on. In the first, we have Rotny-Prager-Yamakawa approximation for the mobility tensor. So this accounts for long-range hydrodynamics. This is suitable to simulate smooth colloidal particles and particles with brushes where the lubrication forces are not important. Long-range hydrodynamics is good enough. And in the second module, we have, in addition to the long-range hydrodynamic interactions, interparticle lubrication, which is implemented using the exact solution to hydrodynamic resistance derived by Jeffrey and Onishi. In case of squeezing particles towards each other, the resistance scales with 1/h, whereas when the particles are sliding over each other, the resistance scales with log 1/h. And this module is suitable to simulate smooth solid particles where the lubrication may be important. And the third module we have simulates the rough surfaces of the particles, in which we implemented the John Brady's hydrodynamic friction model along with the long-range hydrodynamics and lubrication. The idea here is when the rough surfaces are sliding over each other, locally the fluid is still getting squeezed. So instead of having log 1/h scaling for this sliding resistance, here we use 1/h scaling for the sliding resistance. So the sliding resistance terms are now replaced with these functions shown here. We wish to compute the gels produced by these 3 modules and compare them against each other. Since we are simulating depletion gels, we also have interparticle potentials. We use hard sphere potential to avoid particle overlaps. The short-range depletion attraction due to the presence of non-absorbing polymer in the suspension is modeled using Asakura-Osawa potential. The electrostatic repulsion due to surface charges is modeled using Yukawa potential. The typical potential curves are shown here. Black curve is the net of attractive and repulsive potentials, and the black curve has a kinetic barrier. Brownian energy or the applied shear can push these particles over this kinetic barrier to make gels. Since we are shearing these gels, we have a dimensionless number called Mason number, which is the ratio of shear forces to the attraction forces. Higher Mason numbers here indicate higher shear forces. Here is a typical sheared gel produced with long-range aerodynamics alone. Closer video shows the complex interaction of various clusters. Past researchers in our group showed that this gel microstructure matches well with that of the experimental depletion gels, indicating that the lubrication interactions may not be important. And we will show that it is indeed true. All the gel simulations from this slide on are done for a particle volume fraction of 0.2 and simulated with a 1,000 particle system with periodic boundaries. Let us look at the evolution of gels produced with the three modules. Long-range aerodynamic interactions, second one with long-range aerodynamic interactions and lubrication, and the third, we add friction. Here the Mason number is 0.37. We start with a uniformly distributed configuration in all the cases and look at the evolution over 250 strain cycles. The particles, when you see the video, the uniformly distributed configurations evolve into these different sizes of clusters. And when you look at the terminal state at 250 strain cycles, here the clusters are colored with the size with their size. So you can see the module with the friction produces the smallest smallest clusters, whereas the other two produces larger cluster sizes. To quantify these configurations, we compute different modes of number density fluctuations in the following way. We take a particle configuration and we place a box of the size D at a random location B0 and compute the number of particles in that box. And we repeat this many times by placing the box at random locations many times, and then take statistical average of these quantities n square and n, and then compute the zeroth moment of the number density fluctuations. And this actually gives a measure of heterogeneity in the gel. We can also compute first moment of the number density fluctuations by computing the sum of the distance of particles from the center in the box. And that is this quantity S, and we can compute fluctuations in SX, SX, and SZ, SZ quantities. And using those two fluctuations, we can define an anisotropy factor in the flow vorticity plane, which is defined as Fxx minus Fzz divided by their sum. When this factor is 0, that indicates there is no anisotropy in the XX and ZZ plane, whereas if it is non-zero, there is a finite anisotropy. Here are the plots of number density fluctuations and anisotropy factor evolving over 250 strain cycles for the gels produced with the three modules. Notice that the x-axis is 1 over length scale. In the long-range aerodynamic case, the gel starts with small number density fluctuations over all the length scales, indicating uniform material, and the fluctuations increase at large length scales as the time progresses, finally forming larger clusters here. Interestingly, the gels produced with the long-range HI module and the lubrication module show similar number density fluctuations, indicating that the lubrication does not affect the gel heterogeneity. However, when you look at the gels produced with the friction module, the gels are more uniform. The number density fluctuations are very small. And now let's look at the anisotropy factor. The gels from the lubrication module and the friction module show 0 anisotropy, indicating that the presence of short-range aerodynamics produces more symmetric gels. Whereas when you just have long-range aerodynamics, you can see that the anisotropy factor is non-zero at larger length scales, indicating more asymmetric material or more asymmetric material. Here, now we'll explore the effect of shear rate. What you're looking at is the microstructure after 250 strain cycles for three different strain rates, indicated by the Mason number 0.2, 0.37, and 0.5. So as you go down, the shear rate is increasing, and the gel structures for the three modules are shown here. What we can conclude, what we can tell from this slide is that as you for each of these modules, the gel produced by each of these modules, as you increase the Mason number, or in other words, increase the shear rate, the size of the cluster reduces. And for a given shear rate, the friction module produces the smallest cluster sizes or more uniform material, whereas the other two produces larger clusters and more more heterogeneity. Whereas we can look at this quantified data where we are looking at the number density fluctuations, the 0th order, as well as the anisotropy factor for the terminal state at 250 strain cycles for the gel produced for all three modules. You can directly, it is evident that as you increase the strain rate, the gel number density fluctuations are reducing, indicating that the clusters are breaking up and becoming smaller, and the material is becoming less heterogeneous as you increase shear rate. And again, the gels produced by the lubrication module or the long-range hydrodynamic module show similar results, indicating again that the lubrication does not play a role in establishing the heterogeneity or the cluster sizes. Whereas when you have friction, for all the shear rates, the material is more uniform and very small number density fluctuations exist. The anisotropy factor, when you look at with the lubrication module and the friction module, produces zero anisotropy for all the shear rates, whereas the long-range hydrodynamic module produces a non-zero anisotropy at larger length scales. And it appears to not change with the Mason number or shear rate. One thing I want to point out is the reason we think that we have larger fluctuations for the first two modules and smaller fluctuations with the friction is that without friction, these particles arrange in a compact way into the clusters, giving giving more heterogeneity of the gel. Whereas when you have friction, the particles are particles inside a cluster are in more swelled state because there is this resistance to sliding friction, so they arrange in more swelled configuration, which will lead to less heterogeneity. That's what we think. With that, I'd like to conclude. We have a computed colloidal gel microstructure with the various combinations of hydrodynamic modes, namely long-range hydrodynamics, lubrication, friction. Lubrication does not have a significant effect on the gel microstructure, as we saw. Addition of friction reduces the cluster size significantly, makes the gel more uniform. Increase in shear rate or the Mason number breaks up the gel into smaller clusters. Gel with long-range hydrodynamics display anisotropy. The gels with lubrication and friction showed no significant anisotropy, indicating that short-range hydrodynamics makes gels more symmetric. With that, I would like to thank NSF for funding the project and my advisor, James Swan, and his research group for helping with the work. Thank you. With that, I take questions.